The work I'm going to present you today was done in collaboration with Paolo Perinotti from our group in Pavia, and it's mainly based on this paper that we recently published on the Proceeding of the Royal Society. So, broadly speaking, this is a talk on quantum foundation, and the objects that we want to study are this kind of transformation in which input and output can be quantum transformation themselves. The idea is to generalize the axiomatic approach to state transformation that dates back to Krauss to this hierarchy of higher order quantum maps in order to classify all the maps, all these higher order maps that are admissible in the sense that they preserve the probabilistic structure of quantum theory. Let's review this well-known stuff about the axiomatic approach to state transformation. So, let us consider, say, a map from quantum states to quantum states, and these maps, the most general maps that transform states into states, must obey these requirements. The first one is linearity, because you can imagine to have as an input a convex combination of states, and you want the output to be the convex combination of the outputs, of course. Then you need the requirement that your map, even if you apply locally to a large multipartite state, still outputs a valid quantum state. And this is a non-trivial condition in quantum theory because of entanglement, as we well know. And then you also need some normalization condition that tells you that you will not create probabilities higher than 1. Okay, just from this free physical assumption, you can derive that the most general transformation that complies with this restriction, that preserves the structure of quantum theory, is a completely positive trace non-increasing map in the probabilistic case, or trace preserving map in the deterministic case, or a quantum channel. And moreover, you also have sort of realization theorem that tells you that these mathematically defined, mathematically derived maps have a realization in terms of more physically elementary object, like a unitary evolution that maybe involves some environment that is traced out at the end. Okay, so let's try to generalize this game. And now, instead of having as input and output states, let's consider what happens when we have transformation. So again, we want to identify the most general transformation from a quantum transformation to another quantum transformation, which is compatible with the probabilistic structure of quantum theory. Then, this maps has to be linear for the same reason as before. Again, the input can be a convex combination of channels. And then you need to generalize the notion of complete positivity. It can be a bit tricky, but it's not surprising. The idea is that this supermap must behave well, even if it is applied locally to a large multipartite transformation. This is the generalization of the complete positivity constraint that you have for quantum transformation. And of course, you have to add also another constraint that prevents you to create probabilities larger than 1. Okay. Surprisingly, this is a result that we had a few times ago. You discover that the most general admissible supermap can be realized in a lab as a quantum circuit with an open slot. So the most general transformation that quantum mechanics allows you to transform a transformation to another transformation is something like that. That is, you can do some pre-processing before your transformation, then you do some post-processing. And this is what quantum mechanics allows you to do if you want to transform a transformation to another transformation. Okay, now the question is why we should stop here. You can imagine to generalize this reasoning and considering transformation of supermaps, for example. So this kind of idea goes recursively, and you actually build a whole hierarchy of what we call higher order quantum maps. Okay, the question is why one should be interested in this kind of exotic object. Okay, I will list a few motivations. The first one, probably the most popular, is that when you go up with this hierarchy, there are some new features that appear that are mainly related to causality. Basically, you discover that there is some sub-hierarchy of higher order maps that can be realized as a quantum circuit with open slots. And of course, you imagine something like that. If you have, say, 2 holes, you can fill it, and then you have a map from an object like this dark green to this orange one, and it's fine. But not all the higher order quantum maps that you can define can be realized in this way. A typical example, the first one that was considered, is this quantum switch. It is a map that takes as an input, say, channel A and channel B, and depending on the value of a control qubit here, can output either A after B or B after A. And there is no way to realize this kind of thing as a quantum circuit. The reason is that this kind of maps exhibits the so-called indefinite or quantum causal structure. So there is no way in which you can design this kind of map in such a way that you have kind of a flow, for example, here a flow of information, for example, from left to right. There is no way to do that. They've been studied quite intensively recently, and there are also some claim of experimental realization of that. And moreover, it was also recently proved that if you had access to these higher order maps, you may have some gain, and you may improve some the performances of some quantum information processing protocol. For example, you can enhance channel capacity. And finally, from a foundational standpoint, you may study this extension of quantum theory. And if your framework allows it to do it, compare, say, the higher order quantum theory, compare with the higher order theory of a different theory, for example, of classical theory, of other toy model, for example, to do this trick, this game with Popescu-Hurlick boxes, and compare them and learn more about the structure of quantum theory. So this is why one should be interested in this kind of objects. The problem is that up to now they have been studied as special cases. We were lacking, let's say, a well-defined rigorous framework to study this object. And this is the gap that we try to fill in our work. And how we do that? Okay, first thing to do is to develop a language in which you can address this object. So you give a name to a higher order map. The idea is to define a type system for this higher order map. The idea goes as follows. So you introduce some label for the elementary types, and the elementary types correspond to quantum system, so usual stuff. Okay, just to say that you may have some label, a special label I for the elementary type of the trivial system, the one-dimensional one. Then you may have a notion of parallel composition, and then you have a recursive definition that creates expression of this kind, and which, they are kind of intuitive, that they tell you how this higher order map works, okay? For example, here, the super map that I showed you before is an object that takes as an input something that goes from A1 to B2, and the output is something that goes to A2 to B2. Then, the point now is to generalize the notion of complete positivity in a way that is compatible with this whole hierarchy. And the way to do that, first, we need a notion of, let's say, multipartite higher order maps, a notion of extension of higher order maps. We do that in this way. Again, all of them are recursive definition because we are dealing with this hierarchy of objects. And so the idea is that we can extend any type of higher order map by an elementary type in this way, that if the type is elementary, you adjust the usual parallel composition. So the extension is just considering multipartite system. And if you're dealing with more complex type, you have this recursive definition that actually tells you that you are actually considering extending to a multipartite system the very last output of your higher order map. Like in this case, A to B to C to D, then D becomes multipartite. So this is a definition that allows you to define what is an extended higher order map for the whole hierarchy. Then you may define what is admissible. And the admissibility condition works in this way. Of course, again, a recursive definition. What is admissible at the basis level, so at the elementary level, is just, say, an elementary map. So an admissible map for the elementary system is just a subnormalized quantum state, positive operator, trace less or equal than 1, and the trace equal 1, of course, in the deterministic case. And then, once you define what is admissible at this level, then you can recursively define what is admissible for the whole hierarchy. For example, consider a map M from type X to type Y. It is higher order map of type X, higher order map of type Y. This map M must preserve the set of admissible map of type X for any possible extension E, and maps them to admissible map of type Y for any possible extension E. And moreover, you have this kind of requirement that there exist some other maps that again send admissible to admissible, and they sum up to something that preserves the set of deterministic higher order maps. So this can be interpreted as the idea that M should arise in a higher order quantum instrument. So a generalization is a part of a generalized quantum instrument in this higher order scenario. Okay, these are the definition that we give. And then from this definition, we provide a complete mathematical characterization of this hierarchy of maps. In particular, what we can find, the easiest result is that, not easy to explain, but not easy to prove, is that a necessary condition for a higher order maps to be admissible is that its Choi operator has to be positive. And actually, this tells us that even if you extend quantum theory in this sense, including this hierarchy of everything which is admissible, nevertheless, the only relevant cone still remains the cone of positive operator. And then something that we would like to stress is that this approach actually does not, as it should, does not exploit the mathematical structure of quantum theory, but the, let's say, Hilbert spaces and positive operator enters only at the level of at the basis of this recursive construction, okay? So you can imagine to change the notion of elementary system instead of a quantum system with another one, the one of a general probabilistic theory, and you construct the higher order theory of, for example, for PR boxes, and then you can compare with the quantum one. We have some further result that actually show how you can actually recover all the special cases that were studied in the literature and give them actually their name. In our language, their type of the objects that are studied. For example, so-called process matrices for the one who you knows. We see, for example, that we can introduce a notion of a tensor product between these higher order maps, which is defined in terms, of course, of the elementary operation that we have, but still behaves as a tensor product, commutative, associative. And you have some also carrying identities. Here, identity between types means that you have different label, but they identify the same set of mathematical operators. Okay, this is mainly a sketch of the result that we have, but there is a lot of work that still need to be done. For example, I mean, one could wonder whether in this extended higher order scenario, there exists the higher order counterpart of the control knot. That is a universal set of higher order maps that combining them together generate the full hierarchy. And then, of course, see whether it's possible, you know, to starting from the type to infer, say, the feature of the causal structure of this of the higher order maps of a given type. Okay, I think that that is all I wanted to say. Thank you very much for your attention.
Any questions for our speaker?
So there is some work, I think, from last year by Kissinger and Aulin, where they study causal quantum processes, and they find that the logic of these processes is multiplicative linear logic. That looks a lot like what you had in your second last slide. Could you comment on the relation?
Yeah. I mean, okay, I cannot give a complete answer to that, but actually, what they did was to. Do you know Salinger CPM construction? Okay. The point is that when you're working, let's say, in this category theory formalism, you have trouble working with probabilities. Okay. So what Alex did was try to force some notion of probability of causal structure on top of Salinger CPM construction. What we did is start from a different approach. We don't start from the category theory. We start from a probabilistic theory. We start from quantum theory of states and effects, and then give this kind of recursive definition, and end up with a set of maps, and they coincide with the maps that can be recovered in this other, say, category theory approach.
Thanks.
Other questions?
There's been a lot of work in higher order category theory in regard to quantum mechanics. Are you talking about higher order category theory? Not once was the word category used in your presentation.
Okay. I don't think that this is related to higher order categories. This is what you're asking. So here you always has, there are always properties over a symmetric monoidal category. That's it. Then you endow your category with, let's say, further properties, gadgets, like this guy Alex Kissinger did, but this is not related to higher order category, I think. I mean, I should have to think about that, but on top of my head, I cannot say that it's related.
Okay, we have some time for more questions. So could you comment more on these indefinite causal structures and how they could be physically realized, for example, or found in some of these constructions?
Will you comment? What do you mean? Comment about the?
So in your construction, it seems like when you promote the channels to the states, I could, in principle, allow these indefinite causal structures, right?
Yeah, I mean, the idea is that. Okay, first of all. When you say channels, you have to think, if you think operation is just one use of a channel, okay? So when you start to think in this way, yeah, you may think about a map from tensor product of channel to, for example, a state. And then, say, the order in which you are allowed to use this channel is not defined a priori. Okay, so you may think to use A and then B, or B and then A. And if you allow me to do such a thing, this cannot be reproduced by a quantum circuit in which we have kind of a well-defined error of time. This can be, is exotic if you think that, okay, I have something which is indefinite, I can kind of purify it in the quantum style, and then you have this quantum causal structure. Nevertheless, even if you allow for a convex combination of causal structure, classical, which, I mean, you can do at your home with some, transformation with a piece of wood that you can use only once, and another one you can use only once, costs a toy, I do first this, and then that. Still, this is not, cannot be described as a quantum circuit. And that's why, for example, people like Salinger, Valeron, again, if you want to try to, let's say, to develop a functional quantum programming language, and so you encounter this kind of thing, but you still want to have the possibility of decide which routine goes first, then what down after. Then you need to endow the security model of quantum computation with something more. And that's why they have this work, this quantum lambda calculus, which is a quantum circuit endowed with programmable connection between gates. This is, but if you think that you can purify this connection, then you have even more exotic stuff. I don't know if I answered your question, but this is the landscape of what people are thinking about when thinking about quantum causal structure.
Thank you. If there's no more questions, let's thank our speaker again.
Okay, thanks again to the speakers for all the 3 days, because this ends the scientific program for TQC 2019. You can all give a round of applause.